In the process of hard-coding features, rather than using the conventional game engine, programming proper collisions between entities is a recurring issue. Whether rectangles or circles, it was a challenge to properly implement interactions without frustrating issues recurring like weird clipping and jittering. I've attempted to implement these collisions, I admit, usually in the laziest way possible, numerous times in the past, but they all resulted in some variation of the same project. So finally, I decided to properly design a functional ball engine that can simulate collisions between circular entities. The way I programmed collision response previously was by reversing the horizontal and vertical components of velocity. Because we aren't directly separating the balls through a calculated displacement, but rather through a direction change, the balls would often end up colliding for more than one iteration of the game loop. We are repeatedly inverting their direction of movement every frame they overlap, while failing to separate them. This made collisions look jittery until I rewrote the system to use proper vector math and ball displacement rather than a simple direction change. These vector operations also allowed for smoother movement with acceleration and deceleration regulated by a friction constant. Pygame does in fact have its own built-in vector classes for 2 and 3 dimensions. However, I thought it would be good to implement a vector class from scratch so that the project can be more easily adapted to other languages and frameworks. To simulate more realistic interactions, I introduced a mass property to each ball. Simply, relatively larger objects would be more resistant to external force, whereas smaller ones would respond more readily to a push. To implement this, each ball's mass is calculated as a function of its radius, resembling the volume equation of a sphere or area equation of a circle. R is raised to a lower power to provide a perfect level of responsiveness that prevents larger balls from seeming impossibly heavy. Pi and other constants are omitted since they are cancelled out in the repulsion calculation. During collisions, mass is used to control how much each ball is displaced. The displacement of each ball is weighed by its mass relative to the total mass of the two interacting balls, ensuring that more massive balls shift less, while less massive balls shift more. Later on, instead of instantly displacing overlapping balls, I was able to refine the ball repulsion by calculating their displacements and multiplying the displacement vectors of the balls involved by only a fraction of the total calculated displacement, and repeating this process. With mass, we are able to implement elasticity with a series of calculations involving the coefficient of restitution and impulse. Bounciness is controlled through a predetermined coefficient of restitution, since elasticity can be simulated by determining final velocities from the initial ones. Following real-world physics principles, when the coefficient of restitution is equal to 0, that's a perfectly inelastic collision. When between 0 and 1, an inelastic collision. When equal to 1, a perfectly elastic collision. Additionally, a coefficient of restitution greater than 1 would be considered a superelastic collision. Although not possible in real-world passive systems due to the conservation of energy, we can still simulate super bouncy entities here. Also, if we allow the coefficient of restitution to be less than 0, then objects would pass through each other on collision. By this time, we have what looks to be a fully functional ball engine on the surface. However, there are a few things to optimize. Although the brute force way of collision resolution works with nested for loops, this results in an O of n squared time complexity, something increasingly problematic as ball count increments. So, I use spatial partitioning to reduce the number of collision checks by filtering objects into a grid, then only comparing those in the same or adjacent cells instead of every possible pair. This way, instead of looping through all balls, each ball only checks collisions within its own grid cell and nearby cells, greatly reducing unnecessary computations. Since ball size varies, I partition the map into grid cells of a side length equal to the largest ball's diameter, while checking to see if I need to increase or decrease it with added or removed balls. This is done so that the largest ball can only be hashed to 4 locations at most, which is still manageable. On the downside, adding a significantly larger ball when there are many smaller ones, or clustering many balls together, would reduce the efficiency of the spatial partitioning. This is because more objects would share the same or neighboring cells, meaning more unnecessary collision checks. Optimally, there is a maximum grid size and/or ball size to use this technique to the fullest. I then went a bit further and added off-screen filtering, also known as frustum culling, to skip rendering balls that aren't visible on the screen, using the same spatial partitioning system implemented earlier. By picking out and rendering only balls from on-screen tiles, performance is enhanced by focusing only on what is visible. The full source code is available right now on GitHub, which I have linked down in the description below, with loads of accompanying documentation to provide additional in-depth details. If you like this video, please consider subscribing to the channel to stay updated on future developments.